without any difficulties. And we'll get started in approximately 1.5 minutes. Okay, if you're in the back and having trouble seeing the text or my writing, I would recommend moving up closer to the front, just so that way you're able to follow along with the lecture content. With that said, let's just do one last check just to make sure everyone can observe the material on the screen. Okay, I'm going to turn off the lights to make it a little bit more visible, and then we'll continue on with the lecture. Okay, perfect. So when we last left off, we were doing density calculations. So as we discussed, you can measure the mass of an object using a balance. Now, commonly in the lab, especially for liquids, you can't just put a liquid straight on the balance. You don't just put materials or solids directly on the balance, right? So then, we often end up weighing objects via difference. So what do we mean by weighing by difference? So let's do this with some pictures. In this case, a known volume of liquid is added to an empty pre-weighed container. And to calculate the mass of your sample, so the mass of your sample is equal to the mass of the container plus sample minus the mass of the container. Right? Since any mass that is not made up of our container is going to be our sample. So this is a common method. And what type of operation is this? Addition, subtraction, multiplication, division. What is it? Subtraction. So what Sig Fig rules do we have to follow? Decimal places or the Sig Fig rules for subtraction. So let's showcase this and let's draw a picture really to reiterate this point. It's okay, I'm going to zoom in and I'm going to show you a picture of what this looks like. So a student found the mass of a 50 ml beaker to be 22.500 grams. Okay, so I have my beaker and the mass of our beaker is equal to 22.500 grams. Perfect. Okay, next, what we're going to do, and I'm going to use a different color for this, the student added 25.00 milliliters of sample to the beaker using a volumetric pipette. Okay, so then we know that we've used a volumetric pipette with a volume of 25.00 milliliters to transfer liquid into our beaker. Everyone following so far? So we record the mass of our empty container, and now we have a container that contains a known volume of liquid. So let's draw that liquid here. So we're next going to record the mass of the beaker plus the liquid. And in this case, that mass was found to be 47.500 grams. Okay? So in weighing by difference, can we figure out the mass of just the liquid from these two masses? Yes. All we have to do to get the mass of the liquid is you take the mass of the beaker plus the liquid, which is 47.500 grams, and then we subtract from it the mass of our empty container. And what's the mass of our empty container in this case? Yep, 22.500 grams. Okay, now as this calculation is, we have the same ending digit, we can do this manually. Would you like me to show this using a calculator? Let's do that just for consistency's sake. So on our calculator, what we're going to do is we're going to take 47.500, perfect, and then we're going to subtract 22.500, so 22.500, and we end up with the end with 25. Now, we have to be really careful with our Sig Figs here. It's not just 25. If we're following our addition and subtraction rules, how many decimal places do we need to report in our final answer? 3, because how many decimal places do each of these numbers have? 3. Always be careful of that. This is 25.000 grams. Everyone following so far? Does the logic behind weighing by difference make sense to everyone? You will do this a lot in this class. Is there any way for the mass of an object in a container to be less than the mass of the container by definition? No. So oftentimes I see students, they write down their data in the lab diligently, and they somehow report the mass of the liquid in the container to be less than the mass of the container. Always just do a logic check. Make sure that your data makes sense. If you put something in a container, it will have a larger mass than the empty container. Okay, we have the mass, we have the volume. Do we have everything we need to calculate density? Yes, so if density is mass over volume, we have 25.000, and then what's our volume? Yep, 25.00 milliliters, okay? Now, 25 over 25 is going to give us 1, but I'm concerned about Sig Figs. How many Sig Figs do we report? We are dividing two numbers, right? So what rules do we need to care about? What do we need to care about? Decimal places or Sig Figs? Sig Figs. This top number has how many Sig Figs? 5. This bottom number has how many Sig Figs? So how many Sig Figs should our answer have? 4. So the density at the end of our calculation, our density is going to be equal to 1.000 gram per mil. 4 Sig Figs. So a lot of the times when I ask you a density question, when you're asked to calculate density in laboratory, you're going to need to make sure you're following the Sig Fig rules. Otherwise, your answer will be marked incorrect. This is a common thing I see in Canvas. Oh, I entered in the right number, but Canvas marked it wrong. It's because it has the wrong Sig Figs, and I'm looking for Sig Figs on the Canvas quizzes. Does that make sense? Okay. So let's have you now do an example. So in this case, we measured the mass of our beaker. I'm just transcribing the data to make it easier on you for those in the back. We found the mass of the beaker to be the following value. The volume of liquid. For someone in the front, would you like to volunteer and tell us the volume of liquid? How much in this example? How much did we actually add to our beaker? 10. Yep. So we added 10.00 milliliters. The key word is added and then a volume. Okay, and then the mass of the liquid plus the beaker. Reading off the problem, what did we find the mass of the liquid and beaker to be? Yep, 35.600. Okay, so from this information, I'd like you to calculate the density of this liquid. Oh, these examples aren't done directly from the document. These are supplements for the exercise. Any questions? Okay. Any questions? Any questions? Okay. Would anyone like to volunteer a response for this question? Would anyone like to volunteer a final density calculated for this question? Or do you want a little bit more time? Okay, no problem. And if you have any questions, don't be shy to raise your hand. Yes. Sorry. Oh, no, no problem at all.
So it's
Yep, exactly right.
this 4-6
Yep, exactly right. Yep. And remember to include them. Any questions? Yep, exactly. So I've seen a lot of reasonable responses, so let's discuss this together as a class. So what's our first order of business? How do we calculate the mass of our liquid? Can we calculate it via difference? Yes, right? So what two values do we need to calculate our mass?
The mass of the beaker and
Yep, the mass of the liquid and beaker, and what else?
the mass of the beaker.
The mass of the beaker, right? So to calculate the mass of our liquid, what we're going to do is we're going to take the mass of our liquid and beaker, which is 35.600 grams, and we're going to subtract from it the mass of the empty beaker, which is 15.600 grams. Now, of course, in these examples, I've made the numbers a little bit easier, so that way we don't have to break out our calculator every single time. But I want you really to focus on what do we care about when we subtract these numbers? Decimal places. So we want to retain the least number of decimal places among these two numbers, which is 3. So we get, in the end, 20 point, and how many decimal places do we need to report? 3. So this would be 20.000 grams. Perfect. Now, if density is equal to mass over volume, let me rewrite this over here. If density is equal to mass over volume, do we know the mass of our liquid? Yes. It's 20.000 grams. And do we know the volume of our liquid? Yes, 10.00. So punching that into our calculator, we get 2. Like 20 over 10 is 2. But that's not really the important part of this problem. The important part is how many sig figs you report. And when you divide numbers, what do we care about? Sig figs. So this top number has how many sig figs? 5. The bottom number has how many sig figs? 4. So how many sig figs do we report? 4. Exactly. So that gives us 2.000 gram per milliliter. Does that make sense? Okay. I see a lot of error in density calculations. Mainly, students often use the mass of the liquid and beaker in the density calculation and end up with a very large number. Okay, now this is just one way of figuring out the volume of a liquid. We can use a piece of volumetric glassware. The other method, and this is primarily applied to solids and irregularly shaped solids, is called the water displacement method. So I'm going to draw a picture of it because it's intuitive if we start to think about it from a real world perspective and from our life experiences. So if you've ever taken if you've ever been in a pool, or if you've ever taken a bath in a bathtub, what happens when you step into that bathtub? What happens to the water level? It rises, right? So a key idea in the water displacement method is that objects will displace a volume of water equal to their volume. So to showcase this, let's suppose we have a piece of metal that has a volume of 1 milliliter. We won't know this at the onset, but I'm telling you its volume is 1 milliliter, so we can see how water displacement works. Okay, next, we're going to have a graduated cylinder. So this is going to be our graduated cylinder. It's going to be our cylinder. And it has various markings. So 5, 10. And now I'm going to draw the water level. So let's suppose our water level from the bottom of our meniscus is around 5. So our V initial is 5.0 milliliters. And yes, this is to the right number of sig figs. Okay, what would we expect to happen as we drop our metal block, into this graduated cylinder? Would we expect our water level to rise or fall? To rise. And by what volume will our water level rise? 1 milliliter. This cube is going to push water out of its space, and the water level will go up 1 mil. So in turn, just showing an after picture, let's draw the same graduated cylinder. Maybe not quite the same one. Let me draw that a little bit better, so that way our pictures are consistent. 1, 2, 3, 4, 5. So here's the 5 mark. 6, 7, 8, 9, 10. Okay, and our water level, now that we have this cube sitting in our graduated cylinder, our water level has risen from 5 mils to 6 mils. So our V final is 6.0 milliliters. So by inspection, can we see that the difference, but what's 6 minus 5? What's the difference in our water volumes? 1 mil. And does that 1 mil match the volume of our object? Yes. So the key principle behind the water displacement method is by measuring the volume in a graduated cylinder before and after an object is added, we can calculate the volume of any object. Does that make sense? Now, there are a few limitations to this. One, the object can't dissolve in water. You can't do this water displacement method with a sugar cube because the sugar cube will dissolve. It only works for insoluble materials, mainly metals. So, the key thing that we've taken away from this discussion is that the volume of our solid is equal to the volume final after we've added the solid minus the volume initial, which is the volume of water before we've added the solid. Now, since density is mass over volume, all we're doing is for our volume term, we're plugging in this expression, right? This is how we've calculated the volume of our solid object. Does that make sense? Let's show a few calculations involving this method. And again, I just can't stress enough, be careful with significant figures. Density is a division operation. This calculation for the water displacement method is what kind of operation? Subtraction. So make sure you're following the Sig Figs rules for each. So let's keep going. And you're going to be asked to analyze pictures similar to in a laboratory setting. I mean, chemistry is a practical science. Whenever possible, you'll be shown pictures of reactions, pictures of experimental setups, pictures of data collection methods, and pictures of instruments. So in this case, we have two graduated cylinders. This is our before picture. This is our after picture. So if we utilize the water displacement method, our goal is to record the volume initial and the volume final. And from these two volumes, we can calculate the volume of our solid object. So, working together now, what's our first order of business? Can I just write off the volume straight away? Do I have enough information to write off the volume straight away? No. In terms of your procedure, you first need to figure out what do each of these little tick marks represent and how many digits can I actually report? So, to go from 9 to 10 milliliters, it takes us 1, 2, 3, 4, 5, 6, 7, 8, 9. It takes us a total of 10 of these little tick marks. So in 1 milliliter, it takes us 10 ticks. Does that make sense? Does this look familiar to everyone? So then we know that 1 tick is equal to 1/10 of a milliliter, which is 0.1. So we know each of these little marks is 0.1. We're making progress. We also know from the perspective of significant figures that 1/10 of a tick is 0.1 divided by 10, which is 0.01 milliliters. Does that make sense? You always want to do this analysis before you report a measurement, as this is the way to help avoid errors. The last thing I want is for you to make an incorrect measurement and then the rest of the problem gets thrown off. Okay, so to clear up some space now, we're now ready to start taking a measurement in this system. So, as this is a graduated cylinder, it's read from bottom to top. So then, if we are somewhere around the second mark before 9, what does that second mark represent? 8 point. So what does this second mark represent? What was that? 8.80, exactly right. Or 8.8. So that mark represents the certain digits of 8.8. And reading from the bottom of the meniscus, are we pretty close to right on the line? Are we pretty close to smack dab on 8.8? Okay, so we're allowed to report a volume initial of 8.8 as our certain digits. And then are we allowed to estimate an additional digit? Yes, so we can estimate that last digit in the hundredths place to be what? 0. Yeah, that's fine to estimate. So this is 8.80 milliliters. Now, do I have to do this same tick analysis for this second graduated cylinder? We should, but do we have to actually do any new work? No, it's the same graduated cylinder, right? It has the same graduated marks. It should be the same instrument. So it has the same uncertainty, and as a result, we're going to report a similar number of decimal places and a similar number of significant figures. Okay, reading, we're somewhere between 10 and 11, and we're at the 1, 2, 3, 4, 5, 6. We're somewhere past the 6th mark. So we're between the 6th and 7th mark. So what are our certain digits? If we're past the 6th mark, what do we know for sure? 10.6. Yeah. So we definitely know 10.6 are our certain digits. We're past the 6th mark and we're past the 10 major mark. Now, can we estimate an additional digit? Yes. And we're not quite on the line in this case. Is it closer to 6 or 7? 7. So what would we like to estimate it to be? Sure. 10.68, that's perfectly fine. Okay, perfect. We now have our initial and final volume measurements. So just to reiterate, our V initial is 8.80 milliliters, and our V final is 10.68 milliliters. So do we have enough information to figure out the volume of our solid? Yeah. All we have to do is subtract these two numbers. So the volume of our solid is equal to 10.68 milliliters minus 8.80 milliliters. And again, following our Sig Fig rules, what do we care about when we're subtracting numbers? Do we care about Sig Figs or decimal places? Decimal places. So how many decimal places should our answer have? 2. Perfect. So let's break out our calculator for this. So we have 10.68 minus 8.80. We hit the equal sign and we get 1.88. Okay, perfect. We're on the same page on that. So the volume of our solid is 1.88 milliliters. Perfect. Now, if we know the mass of our solid, we found the mass of our solid to be 16.91 grams, do we have enough information to calculate the density? Yes. So density is equal to mass over volume. So we plug in our mass of 16.91 grams and our volume of 1.88 milliliters. And punching that into our calculator now, 16.91 divided by 1.88, and we get a very large number, or a very long number with a lot of decimal points. Okay, so let's write that down. So we have 8.9946. So we have 8.9946 gram per mil. We're not done. We're going to need to round to the correct number of Sig Figs. And looking at this division operation, what's the least number of Sig Figs? How many Sig Figs do we need to retain? 3. So let's look at our third significant digit. We look one space to the right. Is 4 greater than or less than 5? Less. So then we round down. And that gives us a density of 0.99 gram per mil. Now, of course, if your volume estimated digit is a little bit different, this number may be a little bit different. The key thing, you should always retain the correct number of significant figures from each step. And in the end, no matter how you estimated the volume estimated digit, you will end up with the same number of significant figures in your answer in 99% of the cases. Any question on the water displacement method? Yes. Sure. To the volume measurement section? Yes. Perfect. And again, do not assume all graduated devices have the same tick mark distribution. We will purposefully, in some labs or in some practicals, give you a graduated cylinder that has 2 milliliter increments, or a 10 mil graduated cylinder that has 0.2 milliliter increments. So always go through and just check to make sure that your readings match the instrument that you're taking the readings from. All good? Okay, perfect. So let's have you do a few more examples. And I really like this example since this is something that you'd actually see in your real life laboratory application. In this case, you're performing a density determination on a set of 3 marbles. So not just a single marble, but 3 marbles. I've given you the mass as 97.394 grams. And what I want you to tell me is from these 2 pictures, what is the density? So to alleviate this process and to make it easier to see, I'm going to zoom in on this picture. Did everyone have the guidelines of this question written down? I'll give everyone a moment to do that, and then I'll zoom in on the picture so you can start taking some measurements. All good? Okay, I'm going to zoom in and I'm going to give you approximately 5 to 10 minutes, and I'll be walking around, and I'd like you to tell me what is the volume of these 3 marbles, and then from the mass data, I'd like you to tell me the density. Again, remember my warning about graduated devices. They're not all the same. Any questions? Everything going on? Any questions? Okay. Everything going okay? Yep, looks good so far. Ah, okay, yeah, that's fine. That's fine. Yeah, yep, that looks good. Yeah, okay, that's fine. Everything going okay? Let's see. What were the 60 come from? Yes, but what does each of the little tick marks represent? A tenth. Yes, yes. It's okay. Any questions? What do you measure so far? Okay. It's close to 60, but what do each of these little tick marks represent? 2. Yeah. It has to go up to 0.2. Okay. Yeah. Any questions? Yep. The main thing is you want to make sure so the following Sig Figs rules associated with graduated gas. A little bit.
a little bit. Because the meniscus label it's a little. Your number doesn't need to be spot on. It does need to have the right person. So that's what this problem is. Any questions? Yes, that's very close. How do you write it? So the number of Sig Figs is correct. So 1 million is, so it's 1 million. So 1 to 7. So then it should be a little hard. It's not actually but the Sig Figs are so we just approximated ourselves.
So we can do one more.
Any questions? How much did you decide it took?
5.
Yep. Any questions?
As far as like the techniques.
So one. So to go 20 minutes, each
It's almost.
Oh, it's almost 100. Yeah. But on a larger district. Figure out a standard distance.
Yeah, I'm going with
Figure out that. Yes.
So, as you can see, this problem has some subtleties attached to it. First and foremost, just to show you how I would solve it as an instructor and like an ideal solution for a student. So to go from 50 to 70, so in 20 milliliters of volume, if I count each of the marks, it takes me 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 marks. So it takes us 10 tick marks. So then 1 tick is equal to 20 over 10 or 2 milliliters. Does that make sense to everyone? Okay. Next, we figure out the maximum number of digits that we can report, or 1/10 of a tick is equal to 2 over 10, which is 0.2 milliliters. Perfect. Just a side note, if 1/10 of a tick is even, you can only report in increments of 1/10 of a tick. Like I can't say 60.1, for example. It has to be an even number. So next, we're going to take our volume measurements. So for V initial, from the bottom of the meniscus, we are slightly past the 5th mark and under the 6th mark. What does that 5th mark represent? If we're 5 ticks up from 50, 60. So our V initial is about 60, These are our certain digits. And what digit can we estimate? Would someone like to propose an estimated digit? 0.2. Yep. So we have 60.2 milliliters. Now, after we have added our marbles, we can figure out our V final. It's the same graduated cylinder, so this same tick mark framework applies. Now, we are past 90 and we are 1, 2, 3, 4, 5 ticks past 90. Yeah, 100, exactly. And can we estimate an additional digit? 0.0, sure. It's not quite on the line, but it's within reasonable error. So if you're really close to a line, sometimes there's a small variation in one of the certain digits. Okay, we have our two volume readings. Now all we have to do is take the difference in order to figure out the volume of our marbles. So let's do just that. So the volume of our marbles is equal to 100.0 milliliters minus 60.2 milliliters. Now, following Sig Fig rules, what do we care about here? Decimal places. And how many decimal places should our answer have? 1. Perfect. So let's break out our calculators. Oh, I see. This is the speed. Okay. Here's 2. So we're going to have 100.0 minus 60.2. And that gives us 39.8. So let's write that down. 39.8. Perfect. So we have our volume of the marbles. Do we have from the problem, do we know the mass? Do we know the mass? Yes. So do we have enough information to calculate the density? Yes. So let's switch pen colors for that. Our mass is equal to 97.34. I'm gonna have to zoom up just to make 394. That's why I always like to check my work. Grams, and then divided by our volume of 39.8 milliliters. So for our density, we have our mass over volume. Okay. Now, how many sig figs should I report in my final answer? 3. So let's break out our calculators once again. So we're going to take 97.394 divided by 39.8. And we get 2.447. Now, we're not done. We're going to have to round. So we have 2.447 gram per milliliter. If we need to report to 3 sig figs, where's our third significant figure in this example? 4. We look one space to the right. Is 7 greater than or less than 5? Greater. So do we round up or down? Up. And that gives us 2.45 gram per milliliter. Does that make sense to everyone? Now, let me ask you an interesting question here. This is the density of 3 marbles. Now, my question to all of you is we have the density of 3 marbles as 2.45 gram per mil. So if we have our 3 marbles, that's the density of these 3 marbles. If I wanted you to tell me the density of just a single marble, just one marble, what would the density of 1 marble be? Yes, exactly the same. You don't have to divide or multiply. It's exactly the same density. Why? Density is an intensive property. Does it matter the amount? No. The density of 3 marbles is the same as the density of 1 marble because it has a smaller mass and a smaller volume. This is really the beauty of density, because you can measure the density of very small volumes of liquids and use that to calculate the density of a large volume of liquid. And you don't even have to do any calculation. It's the same density. Does that make sense to everyone? This is a critical point about intensive properties. They only depend on the identity of the object, chemical composition. They do not depend on the amount of material. Okay, any other questions on density calculations? Yes.
So what's a reasonable percentage of error for this?
So what do you mean by per percent error? Like variation?
Yeah.
Typically you observe variation in the estimated digit. So for example, if your number would be 2.45 plus or minus around 0.05. Variation in the last estimated digit.
Right.
And that's not accounting for like inherent, this is more like inherent instrumental error, not necessarily human error associated with reading all of these devices. Yeah. In general, for most labs, you want to be within 5 to 10%. Though some labs you're expected to be within 1 to 5 for if they're very precise techniques. Everyone comfortable on chapter 1? Are we able to move on and start discussing and reviewing chapter 2 a little bit? Okay, perfect. So let's switch now to chapter 2. And again, I highly encourage you, I have all the notes posted on Canvas. Please make sure to print out the notes for each session. The reason why is they have many useful references, tables, and it's really useful when you're solving some of the problems with a lot of parts to them to just have the problem sitting in front of you. You don't have to write anything down, and you can spend more time reading and solving the question rather than writing the question. Okay, so let's look a little bit at atoms and elements, and let's try to talk about the key principles associated with atoms and elements. So first off, we're going to do some review. We've touched on this in chapter 1, and I just want to bring this front and center for chapter 2. Matter, anything that has mass and takes up space, anything with mass and volume, is composed of fundamental building blocks known as atoms. An atom is not the smallest absolute unit of matter, but it's the smallest functional unit of matter for the purposes of chemistry. It's the smallest unit of an element that has the properties and reactivity of that element. So, for example, if we have a giant block of magnesium metal, that block of magnesium metal, here are some, let's look at some properties. This block of magnesium metal will react with oxygen gas. Sure, if you heat a block of magnesium metal, it'll generate a bright light and a lot of heat as it reacts with oxygen gas. Now, if I looked at an atom of magnesium, would you expect that atom of magnesium to also react with oxygen? Yes. An atom is the smallest functional unit with properties and reactivity of that element. So this magnesium atom also reacts with oxygen gas. Perfect. So far, so good. Now, just like atoms, we can string together these atoms to form higher order and more complicated substances, in this case, molecules. So what is a molecule? Molecules are the smallest unit of a substance containing 2 or more atoms bonded together. So a classic example of a molecule, we've actually already brought one up, would be oxygen gas. So in O2 gas, looking at the chemical formula, this 2 tells us we have how many oxygen atoms? 2. So this is a chemical species containing 2 or more atoms bonded together. Now, the atoms involved in a molecule do not necessarily have to be the same. So for example, in carbon monoxide gas, we have a carbon atom and an oxygen atom. Do we still have two or more atoms bonded together? Yes, so it's a molecule. Now, let's move on and let's talk a little bit about elements. So as we discussed last time, the definition of an element stems from the empirical or the experimental method that we isolated and identified elements. So an element, from the empirical definition, is a substance that cannot be chemically decomposed to its component elements. So for example, if we take hydrogen gas, no matter how hard we try, we're not going to get a simpler element than hydrogen in its pure elemental form. Hydrogen can react to make compounds, but we're not ever going to be able to generate a new, simpler element. An element cannot be decomposed to a new, simpler, pure element. Does that make sense, everyone? Okay. Now, element names are derived from their isolation, Greek name, or Latin name. So you may wonder, why does Na correspond to sodium? It's because its formal previous name was natrium. So anytime a symbol doesn't appear to exactly match the element's name, or if it seems like, why is that symbol correspond to that name, has to do with its Greek name, Latin name, or its name obtained from isolation. Now, just to make sure we're clear, as we're going to start to be discussing chemical formulas, each element has a unique symbol. It's 1 to 2 letters, and the first and only the first letter is capitalized. So, for example, CO corresponds to cobalt, an element. Capital C, capital O correspond. How many elements do we have in that description? 2. This is carbon monoxide, which is a compound. So just be really careful with your capitalization. Okay, everyone comfortable so far? Okay, let's keep going and let's start to get to some new stuff. So here we're going to be taking a broader look and we're going to be talking about each of the fundamental experiments that led to the modern view of atomic structure and identification and organization of the periodic table and the elements in the periodic table. So first and foremost, the key principle that was established empirically is atoms of each element have different masses, reactivity, physical and chemical properties. So we can differentiate elements based on their properties and reactivity. The main goal of this next section is to try to identify how did we figure out the composition and structure of atoms? What are atoms made of? So that's our central question. And to really set the stage for this, sorry, one moment. Let's take a look at this quite famous picture of Becquerel's observation of radioactivity. So essentially in this experiment, Becquerel was studying how different substances absorb light and potentially release particles or emit light. In this case, Becquerel was studying a sample of radioactive ore, and he stored the sample adjacent to a pair of photographic plates that were in a separate metal box. So the photographic plate that we're observing here was separated from a radioactive sample, and the sample was completely in the dark. So the photographic plate was not stained by light. Instead, it was stained by something else. And that something else is what we're going to be very interested in this next session. So, to help us understand what Becquerel was observing in this picture, we have to first understand what a radioactive element is. So a radioactive element is a wonderful tool for studying and looking at the composition of atoms because they're an element that is unstable. It's an atom that is unstable. And as a result, they will eject the particles found in the atom into their surroundings. So let's suppose we have a radioactive atom, okay, such as uranium, for example. So it has various subatomic particles, and as it decays, it will shoot out and emit these fundamental particles that make up an atom. So by looking and studying the emitted particles from a radioactive element, where did all of these particles come from? Where did these particles come from? Where were they emitted from? From uranium, and they came fundamentally, what are these particles a part of? What were they a part of before they were shot off? They're part of an atom. So these are the particles that make up or that comprise an atom. Does that make sense to everyone? So radioactive elements are throwing off everything that makes up an atom. And by studying these emissions, we can figure out everything, every single component particle that makes up an atom. Their properties, their masses, their charges. So it's a veritable gold mine. The only unfortunate thing is you have to be someone brave enough to work with radioactive materials on large scale. Okay. So again, just to reiterate, the particles ejected from an atom, these radioactive emissions, are the components of an atom. And by studying radioactive emissions, we can study the particles that make up atoms, our fundamental building blocks of matter. Okay, everyone clear on our goal? Yes.
I was wondering, does that only work for unstable atoms?
Yes. So most stable atoms will not be kicking off protons, neutrons, and electrons. Radioactive elements, due to their composition, they're unstable, and as a result, in order to reach a more stable state, they'll throw off these subatomic particles and generate a more stable element. Yeah. That's more in the nuclear chemistry, but the reason why I'm touching on this and bringing this up is these are really the foundational studies that help us see and understand the composition of atoms.
Do you have for stable atoms different molecular atoms?
Yes, in that case, you have to provoke them and generate an unstable species. But we have plenty of radioactive elements to choose from, and uranium, despite seeming like it's not readily available, there's enough of it to go around for research studies, and the ore is useful enough for this kind of study. So there's plenty of it to lie around. So we often just study these unstable species. Okay. So let's talk a little bit about charge-particle interactions. If there is one part that I want you to take away from chemistry that'll probably serve you well all the way up into grad school, it's this next few statements. Like charges repel, opposite charges attract. That is chemistry in one sentence. That's all we're doing in chemistry. All of the behaviors of these particles can be rationalized using these principles, right? So if we have a negative charge and a positive charge particle, they will attract. If we have two particles of the same charge, such as two positive particles or two negative particles, they will repel. Opposites attract, like charges repel. Does that make sense to everyone? Okay, just always keep that in mind. An additional thing that we need to know is that charged particles are deflected by electromagnetic fields. We'll see this in this next study looking at radioactive emissions. So let's pull up this picture, and this is one of Rutherford's many experiments. It's a wonderfully simple and brilliant experiment in that it provides compelling evidence for the main particles that make up an atom. So in this study, they have a radioactive element. So again, this radioactive element, such as, for example, uranium, is going to be throwing off subatomic particles. It's going to be throwing off the particles that make up an atom. And what we're going to do is we're going to apply a magnetic field. And what this field does is it's going to change how these particles shoot off into space, and it's going to direct the particles based on their charge. So each of these different directions corresponds to a deflection based on charge. Okay, and we can view where the particles deflect using photographic plates. So, with that established, let's now get some ground rules in order for how these different particles behave. Now, we use a general term called ion to describe a charged particle. It can be an atom, a molecule, or a subatomic particle. Anything with a charge is known as an ion. Ions can be positively or negatively charged, and depending on their charge, they interact with magnetic fields in a different way, and they interact with other particles in a different way. Okay? So all of these interactions, all of these deflections are based on charge. Okay? So let's try, before we elaborate a little bit further, let's try to take a look at this picture and what do we see? What do we see? How many deflections do we see? Well, we see, oh, that's very astute to know. We have 2 deflections, and what about the third set? Do we have a set of particles just going straight down the middle? Yes. So we have a total of how many unique types of particles? How many unique paths do we see in this picture? 3. So how many particles that are different do we have inside our atoms? 3. So let's elaborate this, and let's break down each of the following ideas. So radioactive elements will release their component particles, right? So we have these radioactive elements just shooting out particles that are found inside our atom. We see a total of 3 different deflections in a magnetic field. Okay? So we already have this sense that there are going to be 3 different particles. Okay? Looking at these deflections, are 2 of these particles deflected in opposite ways? Do we have one going to the right, the other going to the left? Yes. So these 2 particles, if deflection is based on charge, would they have the same or different charges? Different. So we'll arbitrarily call one plus and the other minus. See, there's a lot we can get from relatively simple experiments. Okay? How would we explain the particles that just go straight down the middle, that aren't deflecting? Neutral, exactly. So plus, minus, and neutral. So in effect, from this experiment, we have this inkling that atoms are composed of 3 different types of particles with a positive, negative, and neutral, no charge. So I boxed this main conclusion in as this is really important. So there are 3 different types of particles that make up an atom with different charges. We have a positive, negative, and a neutral species. Neutral meaning no charge. Just to give you a teaser for this next section, atoms are composed of 3 different fundamental particles. Protons, which are positive, neutrons, which are neutral, and electrons, which are negative. So, in this next section, we're going to talk about each of the experiments used to identify not only the charge, but the mass of each of these particles. And it doesn't take a micro scale experiment to figure this out. You can actually do this using a relatively large apparatus. Many of these effects we can actually observe under, many of these experiments only require observation using a microscope or using the naked eye if you're using the appropriate detector. So let's talk about how we figured out the existence of each of these particles and how we identified their mass and charge. And these experiments were done somewhere around the 1900s, so it doesn't take sophisticated technology to do this. So, first and foremost, let's talk a little bit about the electron. And it's really unfortunate we've moved away from the old school cathode ray TVs because before they updated the TVs, many of the TVs were built on cathode ray tube devices, and people would take them apart and play with the cathode ray beam using magnets, etc. So let's talk a little bit about how we understood and how we studied electrons. So our goal is to focus on electrons, which are the negatively charged particle. So to do this, we're going to look first at a Crookes tube. So what is a Crookes tube? It's an evacuated glass tube that has an electrical charge applied at both ends. You can actually see the transmission of electrons between the cathode and the anode, and we call this beam a cathode ray. So you can see it with the naked eye. If you take apart an old TV, you'll be able to see the actual cathode ray tube and the cathode ray itself. And people, out of curiosity, began studying this cathode ray and these cathode ray tubes, or Crookes tubes. So, now, a cathode ray beam is a passage of particles between two metal plates in a vacuum. Why is this important? Well, these little particles are actually electrons. Now, from this picture, what do we notice that's a little bit interesting about this cathode ray beam? If we bring it up to a magnet, if we place a magnet here, we apply an electromagnetic field, what happens to the beam? Does it change in direction? Does it deflect? Yeah, so before and after, we have a straight beam. We put a magnetic field, the beam deflects. So what does that tell us about the cathode ray beam? Is it charged or neutral? Charged. Okay, perfect. So here are some facts about cathode rays. First, they travel in a straight line. Not very useful. We saw from the picture they're deflected by electric and magnetic fields, and they're deflected towards the positive plate. Okay, so if we have our cathode ray beam and a positive plate, the beam will deflect towards the positive plate. Now, what did I say previously about opposite charges? Do they attract or repel? Opposite charges? Opposites? Opposites? Attract. So then, if it's attracted to the positive plate, what is the charge of that cathode ray beam? Negative, exactly. So from these experiments, we've established that this cathode ray beam is a negatively charged collection of particles, right? So we're going to study this a little bit more. Now, the next main feature, and this really caught our attention, is that these cathode ray beams are capable of moving a small paddle wheel. These cathode rays are composed of particles with mass. So, you can think of a cathode ray beam as a beam of small particles with negative charge. So we're starting really to get a sense and starting to get an idea of the properties of a really fundamental particle. And to reach our final conclusion, these cathode rays are beams of negatively charged particles, right? They're particles, and we call these particles electrons. So this is a wonderful way and a wonderful method that we're able to study and understand some of the properties of electrons. Does that make sense? Okay. Now, we can figure out the smallest amount of charge per mass for the cathode ray. And by studying the collection of particles, by studying this large number of electrons, we can in turn figure out the mass to charge of a single electron, just like we did in our density calculations. We're utilizing intensive properties. Mass to charge ratio is intensive. No matter whether we're looking at one electron or thousands of electrons, the mass to charge is the same. So, in this experiment, what we would do is we would generate a cathode ray beam, we'd utilize a magnetic field, and we'd record the deflection. So this experiment, the main takeaway, you don't need to memorize every single exact detail of this experiment. The main thing I want you to take away from this is by looking at and studying cathode ray beams, we are able to figure out the mass to charge ratio of an electron. We're able to figure out, based on how the cathode ray beam deflects, we were able to figure out the mass of the electron over the charge of an electron. Okay, so that's one piece of data. We aren't quite done though. This isn't enough information to tell us exactly the mass and charge of an electron. So, this next experiment is a really critical experiment that I'd want you to understand a little bit about how it functions and what this experiment accomplished. And this is known as the Milliken oil drop experiment. And this really closed the loop in our study of an electron by elucidating the charge of an electron. And it's really quite an ingenious experiment that you can do with common lab equipment if it's properly prepared. So, in this experiment, it starts by having an atomizer to generate small oil droplets. So up in the top of our setup are a set of oil droplets. Okay, so far so good. We have, and what we're going to do is we're going to pass the oil droplets through a tiny little slit. So we only have a small collimated line of oil drops. Now, from gravity, they're going to fall towards the bottom of this setup. And what we're going to do is we're going to take these oil droplets and we're going to expose them to ionizing radiation. So we're going to take our oil drop, which is neutral, and we're going to expose it to some ionizing radiation. Now what we're doing in this process is we're adding electrons to the surface of our oil drop. And since electrons are negatively charged, what happens to the oil drop? What happens to the charge of the oil drop? Negatively charged, right? So our oil drop becomes negatively charged because it gains electrons. Now, this is not an exact method. It can pick up anywhere between, well, it can pick up a range of electrons. But the key feature of this method is that each different drop will have a negative charge equal to the total charge of all the electrons gained, right? So we can gain 2, 4, 6, 8, hundreds of electrons onto the surface of our oil drop, and the charge of the oil drop will change, right? Looking at this example, 4 electrons has a different charge than an oil drop with 6 electrons. Now, and this is really critical for later on, what unit of charge are we counting in? What is our smallest unit of charge that we're counting in order? What are we adding? What's the charge particle that we're adding? Electron, right? So each time our total charge is based on the number of electrons and the charge of a single electron. So by studying these bulky oil drops that have multiple electrons on their surface, we can look at the charge of a single electron. Now, the way this works is you have an electromagnetic field. So this is a field in our setup. And what this field is going to do is it's going to take our charge oil drop, and depending on how we set our electromagnetic field, the oil drop will either rise or fall. So to use the physics idea of force analysis, the electromagnetic field is going to push our oil drop up and away from the bottom of our container. What is dragging our oil drop down? What fundamental force drags objects down? Gravity. So, looking at our force analysis, we have two forces acting on our oil drop: the electromagnetic field and gravity. The electromagnetic field is based on the charge of the oil drop, while gravity is based on the mass. And if you sit there turning the dial, adjusting the electromagnetic field just right, you'll eventually get it so the oil drop is suspended in air, doesn't move. And we can observe it using our viewing microscope. So once we have our oil drop sitting perfectly still, we have in effect figured out the exact charge of the oil drop. So, just to recap what we're doing here. We take the oil drop, we add electrons to the oil drop. We then look to see what electromagnetic field do we need to have the oil drop stay perfectly still. At that moment, we write down the field strength, and that allows us to calculate the charge of that oil drop. So we're going to do this for approximately 2,000 drops. And we're going to write down our data for these 2,000 drops. And from this large data set, we're going to be able to find some trends. So, first and foremost, because the oil drops become charged by gaining electrons, no matter how many electrons we've picked up, is there going to be a common unit of charge? Is there going to be a common increment? So for example, looking at our example of 4 electrons versus 6, what are we counting in terms? What is our charge based on? So if I add an electron, where does the negative charge come from? From the electron, right? So each time I add an electron, our charge increases by the charge of what? What's our fundamental counting unit? What are we counting our charge in terms of? The charge of an electron, exactly. So then, the charge of the oil drops will be multiples of the charge of an electron. And by studying a large number of oil drops, we can find a common shared charge, a common multiple that is the charge of an electron. Okay, so in a nutshell, these two experiments have allowed us to figure out the mass and charge of an electron, a really, really, really small subatomic particle, to a high level of precision. So just to give you an idea of the mass of an electron, we know the charge to mass ratio, and we know the charge of an electron, so we can calculate the mass. So 1.60 times 10 to the negative 19th coulomb. Okay. Divided by negative 1.76 times 10 to the 8th coulomb per gram. And if we punch that out into our calculator, and it's really important to get a sense of how small these particles are. So 1.60 EE19, oh, negative 19, 1.60 EE negative 19, divided by, parentheses, 1.76 EE8. So we end up with a mass of 9.09 times 10 to the negative 28 grams. Is that a large or very small mass? Oh, sorry about that. So is that a very large or very small mass? Very, very small. So it would be difficult to study a single electron individually, but by studying collections of electrons, we can elucidate the properties of a single electron. Pretty powerful experiments, right? Using relatively simple equipment, we figured out the mass of a particle that we can't even see with the naked eye and is orders of magnitude smaller than particles observable using even the most sophisticated microscopes. Any questions so far? So we figured out the mass and charge of an electron. And what is the charge of an electron? Is it positive or negative? Negative. And our electrons, are they large or small in mass? Small. Very, very, very small. That's what I want you to take away from this. The rest is primarily science history, helping you to understand the historical background of all of these ideas that we discuss in the textbook. Okay. So our next goal and our next set of studies requires us to understand this idea of atomic numbers. So let's start to talk a little bit about how we began to get a sense of what makes an element unique. We know elements have unique properties and reactivity. What we do not yet have a valid explanation for is why, what makes two elements different. And one of the main representative examples of this involves radioactive decay. So, radioactive elements are unstable, and they will emit subatomic particles to generate a more stable atom. One of the common emissions is known as alpha decay, which is a helium nucleus, or equivalent to a helium atom. Now, one of the key features, and the reason why we're talking about radioactive decay, is that when a radioactive element undergoes decay, it loses particles known as protons and neutrons, and it becomes a different element. Now, by studying a wide number of different radioactive elements and how they decay, we began to notice that when the number of protons changes, the element's identity changes. So elemental identity, what makes an element unique, stems from the number of protons that element has. Does that make sense? Okay. So we indicate the number of protons for an element using, you can either describe it as Z, which is named the atomic number. The number of protons, Z, is often described as the atomic number. The atomic number is front and center in the periodic table. So for example, if you look at hydrogen, the number above the element symbol is our atomic number Z. And this represents the number of what fundamental particle? What is the atomic number? The number of protons, exactly. So for example, hydrogen, the element hydrogen, how many protons does an atom of hydrogen have? One, exactly. Good, good. Does everyone comfortable reading the periodic table to identify the number of protons for an element? Okay. So what we're going to do now is we're going to take this a little bit further. And we're going to start to use the idea. We have these protons, we have these electrons, we have the idea that these particles exist. Now let's try to think about how are these particles arranged? How do we put together all of these particles to make an accurate model of the atom? So there are a few major models of atomic structure. The one that was prevalent early on in these investigations into protons, neutrons, and electrons was the plum pudding model. So in the plum pudding model, similar to, for example, like a muffin with berries in it or yogurt with fruit in it, you had a sphere of positive charge, just a blanket region of positive charge, no positive particles just yet, and localized electrons, which are negatively charged. Okay, so that's the plum pudding model. We already just intuitively see a few problems with this model in that we know there are particles and we've seen evidence for particles with positive charge. So having this blanket sphere of positive charge already begins to raise some red flags, right? However, one of the most definitive experiments to help us clarify the arrangement of all of our particles in an atom was Rutherford's gold foil experiment. So here's the plum pudding model. It has some major issues, and we'll see them front and center in this next experiment. So here's the idea of Rutherford's gold foil experiment. So first and foremost, we have a radioactive sample that's emitting a beam of alpha particles, okay? So we're shooting subatomic particles at this gold foil. Okay, now, we're also observing, and we have a detector that will measure the locations that the particles deflect when they hit the gold foil. Everyone okay so far? So we're looking at how do these particles deflect when they impact gold foil. Now, gold foil may seem like a solid object in our day-to-day life, but thinking about it from the perspective of the plum pudding model, we see in reality, we would expect in the plum pudding model, we have this region of positive charge and localized chunks of negative charge. Okay, so here's our plum pudding model. Now, if we take our alpha particle, you can think of an alpha particle as a chunk with mass and positive charge. And if we have our alpha particle attempt to interact or bump into an atom of gold, for example, thinking about the plum pudding model, is there a lot of empty space? Do we see a lot of particles clumped close together in the plum pudding model, or are they pretty spread apart? Pretty spread apart. Using our charge-charge interaction idea that we discussed previously, is this positive charge going to be attracted to these negatively charged electrons? Is there going to be an attractive interaction? Yes. And is this positive charge going to be repelled by this blanket positive charge in the plum pudding model? Yes. So it's attracted to these negative electrons, repelled by this positive charge, and our alpha particle just sort of wiggles its way through, and its path isn't changed substantially. It's not hitting anything. It's not bouncing off of anything. There's no chunk of positive charge for it to deflect off. So for the most part, our alpha particles are just going to go straight through our wall of gold foil, our wall of atoms. And in the end, we'd see the majority of our alpha particles just go straight through the gold foil. Atoms are mostly empty space in the plum pudding model, and our alpha particles can just pass through the gold foil with no issue. Does that make sense? Now, that would be fine, but I'd like to bring your attention to these major aberration events where for some reason, when we shoot our alpha particles at the gold foil, we see a massive deflection. The alpha particle careens off almost back to the original radiation source. So using our idea that like charges, so two positive charges will repel and opposite charges attract. what is responsible for this deflection? What causes our alpha particles to bounce, to deflect? What are our alpha particles hitting? So, what was that? Yep, a positive charge or a chunk of positive charge, such as a group of protons. So, these deflections can best be explained by thinking about it like so. So, in the Rutherford model, we have our atom, and at the center of our atom, we have a collection of positive charge known as the nucleus. Now, atoms still are mostly empty space. 99.9% of all the space in these gold atoms is empty. So if our alpha particle comes lumbering along, for the most part, it's just going to go straight through our atom. Except in the small case where this alpha particle decides, or this alpha particle ends up on a trajectory where it directly impacts our nucleus. And what happens when we have these two positive charges trying to reach the same location? Repel. So what's going to happen to our alpha particle? Is it going to deflect wildly? Yes, it's going to deflect off. And that is what we see here. This small edge case where we see less than 1% of the time a major deflection of our alpha particles is critically important because it tells us two things. One, we have a source of concentrated positive charge at the center of our atoms known as the nucleus. And additionally, we know since this deflection happens less than 1% of the time, what's the majority of the space in our atom? Empty or full? Empty, exactly. Atoms are mostly empty space. Most of the time, these alpha particles just pass right through, except when they hit the nucleus. Does that make sense to everyone? Okay, so just to summarize this idea. So in our expected result, we'd expect our alpha particles to just pass straight through our plum pudding atom. In our Rutherford model, in the majority of cases, our particles pass straight through with no issue, except when our particles hit this chunk of positive charge known as the nucleus. So, in Rutherford's nuclear theory, we have the following ideas. The majority of the volume of an atom is empty space. So just to put this into perspective, if this was the nucleus, if this little dot was the nucleus, where would you expect the outer edge of the atom to be, just to give you a scale? Would you expect it to be 10 miles away? 50 miles away? We have to go somewhere around 1,000 miles away. Atoms are mostly empty space. There's only a small region of the atom where all of our protons and neutrons are located. So most of the atom's mass and all of its positive charge are contained in the nucleus. So the nucleus is a collection and the location of all of the atom's positively charged and neutral particles. And as we established, what do we call these positively charged particles? Protons, yep. So the nucleus contains the protons and the neutral particles, which we call neutrons. Perfect. Now, additionally, atoms are neutral. Overall, they have zero total charge. So there's an equal number of negatively charged electrons and positively charged protons. So to draw that and to help us get a sense of what's going on, suppose for a moment we have an atom with 2 protons. So to match our positive charge, since we have 2 protons, how many electrons would we need? 2. Yeah. So we'd have, surrounding our nucleus, 2 electrons. We have an equal number of protons and electrons. Okay. Any questions before we move on and start discussing protons and neutrons in detail? Is everyone comfortable with the Rutherford model and how it functions? Okay. So let's talk a little bit about protons. So experimentally, they found that treatment of a nitrogen nucleus with an alpha particle ended up with the emission of a positively charged particle with a mass to charge matching that of a hydrogen nucleus. So another way that a proton is written would be H+. So a proton is a hydrogen nucleus. So to draw that out, a proton is a fundamental particle with a positive charge and mass. Of course, just like we did for the electron, we can study and identify the mass to charge of a proton. We won't go into those experiments in detail, just know that we can figure out the mass to charge of a proton. Now, from this information, we are also able to, using similar studies, identify and elucidate the mass of a neutron. So one of the ways that we began to think, the neutron that was often discovered relatively later on in these overall series of experiments, because it's a neutral particle and it's relatively difficult to study and observe the properties of neutral particles. So what they observed when they interacted beryllium with alpha particles is emission of a particle that does not have a charge. And the goal of these next few experiments was to try to elucidate the mass of this neutron. And I'd like you to consult our slide set. And if you provide me a reasonable explanation on how exactly Chadwick's experiment was conducted and how the mass to charge rate, how the mass of a neutron was determined, I'll be able to provide you 2 points of extra credit. We're not going to go into too much detail into that experiment in this class, since it's more just reading for fun. So we've established that there are 3 fundamental particles, and we're able to determine their mass, charge, and mass to charge ratios. So to summarize each of the fundamental particles, each of these subatomic particles, let's take a look. So our 3 fundamental particles are the proton, neutron, and electron. Of course, the electron has a negative charge. The proton has a positive charge. So electrons negatively charged, protons are positively charged. In terms of mass, the majority of particles with mass in our atom, the particles that comprise the majority of an atom's mass, are protons and neutrons. Electrons have a substantially smaller mass and do not contribute in a large amount to the overall mass of an atom. The proton and neutron are the major particles in an atom with substantial mass. Now, there are a few ways of representing protons, neutrons, and electrons. Electrons are often written with an E- symbol. Protons, you can write them as H+ or P+. And neutrons are often written with the N0 symbol. Key things I want you to take away. Where are the protons, neutrons, and electrons located? The protons and neutrons are in the nucleus. The electrons are surrounding the nucleus. The charges, electrons are negative, protons are positive. And the masses, protons and neutrons have a larger mass than electrons. That's what I want you to take away from all of these studies. So from all of these experiments, we've established these parameters for each of our subatomic particles. Now what we're going to do is we're going to talk about how do us chemists indicate the number of protons, neutrons, and electrons in a specific atom. And how do we calculate the number of protons, neutrons, and electrons for a given atom? That's our next goal. So to do this, we utilize what's known as isotope notation or atomic notation. So let's highlight the key features of isotope notation and atomic notation, and let's talk about how to read each component. So first and foremost, you'll see this number in the bottom left-hand corner. This is known as the atomic number. And as we discussed previously, what does the atomic number represent? Yep, the atomic number Z is equal to the number of protons. Let me rewrite this. A little bit strange right now. So this number in the bottom left-hand corner is our atomic number, and it represents the number of protons. Of course, at the center of atomic notation and isotope notation is our atomic symbol. So let's find and let's label our atomic symbol. This is our element symbol. And a critical aspect of this is that from the element symbol, as we established previously, do different elements have different atomic numbers, different numbers of protons? Yes. So then, from the element symbol, for example, if we found oxygen in the periodic table, what atomic number would we see? What number would we see above the element symbol for oxygen? 8, exactly. So, in cases where you're only given the element symbol, can we figure out the atomic number? Can we figure out the number of protons?
Yes.
Yes. So for example, and we'll tab over to the periodic table to show this. If we switch to the periodic table and we zoom in to try to find iron. So we zoom in to find iron. What number do we see above iron? 26. So what's our atomic number? 26. You want to be comfortable accessing the periodic table and reading off atomic numbers from the periodic table. Perfect. Any questions on the atomic number? The new number that we're going to be talking about now is called the mass number. It's found in the upper left-hand corner, and the mass number is often abbreviated with the symbol A. Now, what does the mass number represent? The mass number is equal to the number of protons plus the number of neutrons. It's a sum of all of the particles with large masses in our atoms. We aren't concerned too much with the mass of electrons because they have a relatively small mass. Not negligible, but quite small. So the mass number A is the total number of protons and neutrons. We can use the mass number to figure out the number of neutrons found in our atom. And let's show how we would do that. So the number of neutrons is equal to the mass number minus the number of protons. Does that make sense to everyone? We just rearrange this equation. So, for example, we'll do some calculations in a moment. but just as an example, if we are looking at oxygen 18/8, reading off from this isotope notation, as we established, this number in the upper left-hand corner is known as what? What's the number in the upper left-hand corner? That's the mass number, okay? So then, if we want to figure out the number of neutrons, we take our mass number, which is 18, and then as we established previously, the number in the bottom left-hand corner, 8. What is that representing? That's the atomic number, which tells us the number of protons. So if we wanted to figure out the number of neutrons in this specific atom, our number of neutrons is equal to the mass number minus the number of protons. So in this case, we have 10 neutrons. Does that make sense? Okay. Now, let's talk a little bit about the charge. Let's talk a little bit about the charge. And we're going to zoom up in a moment and take a look at these two isotope notation symbols. And let's try to identify the charge in each of these. So let me switch pen colors for that. And looking in the upper right-hand corner, we see two numbers. They can be either positive or negative, and this number represents the charge. Now, the total charge of our atom is dependent on the number of protons and electrons in our atom. So to write a full expression for charge, the charge is equal to the number of protons minus the number of electrons. So essentially what we're saying in this charge calculation is we're adding up the total amount of positively charged particles and then subtracting out our negatively charged particles, right? So depending on the charge, we classify different charged atoms or ions as either cations or anions. So if we observe a positive charge, we call the species a cation. If we observe a negative charge, we call the species an anion. Anions are negative, cations are positive. So let's delve into isotope notation in a little bit more detail. So just as a refresher, a cation is a positive ion. And let's try to think this through. When we see a cation, are we going to have more positive protons or more negative electrons in our atom? Will we have more protons positive or more electrons negative? Protons, yep. So a positive ion, we have more protons than electrons. An anion has a negative charge. It's a negative. One moment. It's a negative ion. So would we expect to have more negative electrons or more positive protons? Yep. So we have more electrons than protons. Okay, now with all of these definitions in mind, we can utilize a much more user-friendly definition of elements using isotope notation. So the way I like to think of elements are substances whose atoms all contain an identical number of protons called the atomic number. So if two atoms have the same number of protons, the same atomic number, they're the same element. Each element has a unique symbol with a unique atomic number. So I don't need to give you the atomic number in many cases. You can find it using what resource? What resource do we rely on? Periodic table, exactly. So you're going to use the atomic symbol and the periodic table. So as we established previously, looking at our periodic table for iron, for example, if we zoomed in on iron, we found iron had an atomic number of 26, right? I'd like for you to now take a look at chlorine, break out your periodic table. There's also one in the back if you do not have one handy, though I do recommend bringing a periodic table to class each session. And I'd like you to tell me what atomic number should I fill in for chlorine. We know iron has an atomic number of 26. What is chlorine's atomic number from the periodic table? Just take a moment, and if anyone would like to provide a suggestion. What was that? 17, exactly right. So let's show how we obtain that. If we flip to our periodic table and we go to chlorine, what is the number above chlorine in the periodic table? 17. That's the atomic number. There we go. We found it using the periodic table. Perfect. So we know that chlorine, has an atomic number of 17, and chlorine has 17 protons. Iron, with an atomic number of 26, has 26 protons. Perfect. Let's talk a little bit about species with different numbers of neutrons. Let's talk about those. So in the periodic table, as we discussed, if you look up chlorine, the number above the element symbol is our atomic number. In this case, the atomic number, which is equal to the number of protons, is equal to 17. You really want to be comfortable utilizing the periodic table. It's a very information-rich document, and you want to make sure you're comfortable using the one that I'm going to provide on your exams. And I've attached copies of it in your notes and on the slides. Okay, so with that established, here another copy of the periodic table is available in the notes. Let's now talk about what happens when we have atoms of the same element, same atomic number, but with different mass numbers, different numbers of neutrons. So in this case, we're comparing oxygen 18 and oxygen 16. As we notice, are our atomic numbers the same? Yes, atomic number 8. So these atoms are the same element. However, taking a look at our mass numbers, are our mass numbers the same or different? Different. Now, as we discussed previously, the mass number is equal to the number of protons plus the number of neutrons. So then, if we have the same atomic number and different mass numbers, what must differ? What's different between these two atoms? Neutrons. They have different numbers of neutrons. So just to showcase that, to calculate the number of neutrons, all you do is you take the mass number and then from that you subtract the number of protons. So let's do a sample calculation for each of these two isotopes. Again, isotopes, same element, different mass. They have very similar properties, but slightly different masses. So let's take a look at oxygen 18/8. So if we wanted to calculate the number of neutrons, what is our mass number? 18, yep. So all we're gonna do is we're gonna plug in 18. And what is our atomic number? How many protons are we dealing with? 8. So we take 18 minus 8, and that gives us 10 neutrons. Perfect. Now, just to reiterate, from the atomic number, so if we have the atomic number or the atomic symbol, that tells us the number of protons. From the mass number, those two pieces of data together, the mass number and the atomic number, or the atomic symbol, allow us to calculate the number of neutrons. So what I want you all to do now is to take a look at the following symbols in isotope notation, and I'd like you to calculate the number of protons and the number of neutrons in both of these two atoms. And you'll need the periodic table. Any questions? Oh, all set. Yeah. So I saw a lot of reasonable answers. So first and foremost, we need to fill in our atomic numbers. So for bromine, if we go to the periodic table and we find bromine, the number above bromine is 35. So we have an atomic number of 35. Perfect. Okay. Doing the same thing for magnesium, breaking out our periodic table. If we go and find magnesium, what is magnesium's atomic number? 12. Okay, perfect. So from here, we know that the number of neutrons is equal to the mass number minus the number of protons. So given that, the number of neutrons, what is the mass number for bromine? 79. What's the mass number? 79. And how many protons do we have? 35. So that gives us 44 neutrons to work with. For magnesium 24, our number of neutrons is equal to our mass number, which is 24, minus our atomic number, which is 12, giving us 12 neutrons remaining. Does that make sense to everyone? Okay. There's one more calculation I want us to be comfortable with, and then we'll be able to continue this on next session. I want to make sure we cover this as a complete chunk, so that way you can practice it as a cohesive unit. Okay, so let's take a look at the following example. And what I want you to do this time is, instead of calculating the number of protons, neutrons, and electrons, I'd like you to convert the number of protons, neutrons, and electrons into isotope notation. So you're doing the same process, but backwards. And then I'd like you to tell me what element has only one proton. So take a moment to work on that. And I just want you to be comfortable writing out isotope notation symbols. So this may seem like a bit of an odd example, but there's one key feature of hydrogen isotopes that I need to talk about. So again, just as a little spoiler, what element has only one proton? What element has an atomic number of 1? Hydrogen. Yep. So these are all hydrogen atoms. In the first example, how many protons do we have? 1. We have 1 proton. We have 1 proton. And how many neutrons do we have? 0. Yep. So then, if we're calculating a mass number, we have a mass number of 1. So we'd write this as H1. Your typical hydrogen nucleus. In the second example, if we're calculating the mass number, we have how many protons? 1. Yep, we have 1 proton. And how many neutrons? 1. 1 plus 1 gives us 2. So what is our mass number? 2. And for the third example, we see a total of 2 neutrons and 1 proton. So what's our mass number? 3. So these are all isotopes of hydrogen. The reason why I bring this up is hydrogen is one of the only elements where its isotopes have unique symbols due to their prevalent use in both medicinal studies, biological studies, and in structural studies of molecules. So the H2 nucleus is abbreviated as D, or deuterium. So this is still elemental hydrogen. It's just a specific isotope of hydrogen with a mass number of 2. Likewise, H3, which is not often brought up, it's pretty expensive to make, is abbreviated as just the symbol T for tritium. Just make sure you can recognize deuterium if it comes up on later questions, as it's often a nice way of testing conceptual understanding. Replacing deuterium for hydrogen doesn't change a lot about the molecule, but it does change its mass. So it's a way of generating heavy compounds. Everyone okay with this example? Okay. Let's now cover the last point, and involves a discussion of ions. So in ions, we have the same element, atomic number, number of protons, but a different charge. And when you observe ions, if it has a different charge and the same atomic number, this is telling us bright and clear that we have a different number of electrons. So ions, same element, different number of electrons, different charge. Again, anions are negatively charged species, while cations are positively charged species. To reiterate, for our charge calculations, the charge is equal to our number of protons minus the number of electrons. So then, if we rearrange this equation, since we can figure out the number of protons really easily, right? We can just look it up. So rearranging to solve for the number of electrons, we get the number of electrons is equal to the number of protons minus the charge. Important things to keep in mind here. Important things to keep in mind for this calculation. First and foremost, this charge, you need to make sure you're inputting in the calculator with the right sign. If I have a positive charge, you plug in a positive number. If we have a negative charge, what number do we plug in? Negative number. Okay, perfect. So let's do an example set of calculations. First and foremost, let's look at S2 minus 32. And first and foremost, we need to figure out the number of protons. And to do that, where do we need to go? Periodic table. So I'm going to break out the periodic table, and I'm going to go find sulfur. What number is above sulfur's atomic symbol? 16. So how many protons do we have? 16. I know it may seem silly for me to flip to the periodic table every single time, but on an exam, you want to make sure this kind of process is almost muscle memory. So we have an atomic number of 16. Our number of protons is equal to 16. What is the charge for this molecule? What is our charge? Yep, our charge is -2. Just as a side note, most charges are written with the number before the charge. We'll see later on when we talk about oxidation numbers. There's no reason why you write this as 2 minus or a -2. It's just convention for chemistry, in case you were curious. Okay, so do we have enough information to calculate the number of electrons? Yes. Okay, so then solving that, show that in a different color. So our number of electrons is equal to our protons, which is 16, minus the charge, which is -2. That gives us for our number of electrons. If we're subtracting a negative number, that's the same as addition. So 16 plus 2 gives us 18 electrons to work with. Just as a bonus, to make sure that we're 100% comfortable, do we have enough information to figure out the number of neutrons? Do we have enough information to figure out the number of neutrons? Yes. So to do that, we take our mass number, which is 32, minus the number of protons, or our atomic number, which is 16, and that gives us 16 neutrons to work with. Perfect. So now we're starting to tie everything together. Let's do another example, and let's look at potassium 39 plus. So I'd like you to take a moment and work on that example. Potassium 39 plus.
That's one of the. Oh, it's on campus. Oh, under module. Okay, each of the main sets are done. And the self-see pop up on each of the.
I can now memorize all.
Oh, no, you don't have to. I mean, your views have to come through. Reading if you're all and ACS. And it's exactly what they need. What you know you can. Yeah. Any questions?
No.
Okay, perfect. So let's talk about this example. So going to the periodic table and finding potassium. I just want to reiterate, you don't have to memorize every single atomic number. You do have to know how to use the periodic table. And as we see, potassium has what atomic number? 19. So let's go to, okay, so our atomic number is 19. So our number of protons, let's keep my color scheme consistent. So number of protons is equal to 19. Let me write this in the right color. Okay, what is our charge? What is our charge in this case? What is our charge? +1, exactly right. Okay, so then if we want to figure out our number of electrons, our number of electrons is equal to our number of protons, which is 19, minus the charge, which is +1. So 19 minus 1. So that gives us a total of 18 electrons to work with. Does that make sense to everyone? Okay. Finally, to finish off this problem, and as our last example for this session, our number of neutrons is equal to the mass number minus the number of protons, or 39 minus 19, which gives us a total of 20 neutrons. Any questions on this example? Okay, that is the end of this in-lab lecture. We'll do additional examples next session. Oops.